The need for numpy, the way to represent the series of numbers, one-dimensional, two-dimensional, any dimensional, so that each element is known to be a number from a known limited range. So this allows a far more efficient representation than the heterogeneous and flexible Python list that has to use more bits than strictly speaking are needed to store the elements to allow for all of this flexibility. So in this lecture I can only scratch the surface of numpy just to show what the general idea is. So when using numpy, so surely we keep this numpy reference. So in numpy, so this is the data type, the numerical vector or a matrix, and then list of all the functions that you can apply. And numpy, so then it's is the foundation that whole bunch of other things are built on. And scipy, so if the Python math module was the numerical high school mathematics, so this looks like numerical mathematics at the college undergrad math and engineering. So all these things that are needed in science and engineering numerically, numerical integration, optimization, various transformations and matrix stuff. So all the sciences can productively use these things. So so lots of people created this, that scientists don't need to be data experts. They can just use these known algorithms to deal with their data. So let's look at this numpy principle now. Let's play around here in the repo. Let's see what is gonna happen. So we start by importing numpy, and then we create the numpy vector or a matrix. But let's we previously created an A range. We could create from any list, but let's do something interesting. So the whole bunch of sub modules in there. So np random and the Poisson distribution. So distribution that basically like if a hockey team on average scores 3 goals per game, so how many goals can they score? Theoretically there's no upper limit, so but the Poisson distribution often a good way to model this kind of thing. So np random Poisson, so the Poisson distribution parameters, so 3 on average, and then we can get we give the current size. So let's make a 4 by 5. So you can make any number of dimensions. So I'm just gonna use up to 2 dimensions because I don't know anything about the tensors. So 2D is a matrix, and then I don't know how to visualize them easily anyway here. So let's create the numpy array. Looking at what it is, so it is an array of integers. Let's ask it, so all these numpy properties, what is the element type? So the element type is int 64, so assigned integer of 8 bytes, so a bit of error in there, but so the whole bunch of random samples. So if 3 on average, so sometimes we get less than that, and sometimes we get more. Sometimes theoretically we could way more, but those are gonna be exponentially rare. And let's ask this array, so what shape are you? So it tells us that it is a 4 by 5. So there is 20 elements, and the computer memory addressing is linear as far as we're concerned. So all these numpy arrays in memory, all these elements are stored consecutively. So first we have all the elements of the first row, followed by all the elements in the second row, and then so on and so on. And let's ask, might as well import the sys also. Let's ask what is the size of this numpy array? 272, so 8 times 8 times 20 is 160, so 160 bytes exactly for these numbers, no more and no less. And then the rest, whatever is needed just to be any kind of Python object to begin with. Numpy objects are still Python objects, they just internally access memory directly in a more low-level fashion, but they have all the stuff that makes them Python objects, and even the magic methods from the class, from the next week's lecture, they're properly implemented so that the Python operations do the right thing. But so the data in the memory it's always linearly organized, so it is just that bytes don't mean anything. So this D type and shape, so when you have that block of raw bytes in the memory, there's nothing but the bytes in the memory. We're just saying that we're gonna pretend that those bytes are 8-byte signed integers, and they are arranged in a 4x5 shape. But we can say that these are anything else. So I could say, for example, that I want the shape to be, let's say, 2x10. So the same 20. So now let's look at the array. Now it knows that it's a 2x10. It is the exact same bytes of data in the memory, but we just choose a different way to look at them. And then, so for example, how much is A multiplied by 6? So the result is a numpy array. Notice it's a different one. The original is still there. With the numpy, we gotta be a bit careful with this. Some operations modify the original and some create the new one, and it's not always the same way as it is in the Python list. We gotta be careful here. So here in the numpy demo, where we start by creating an array of doubles. For this is a double burger, or no, it's a double precision floating point. So the 8 bytes, which is like the pretty standard way. So these decimal numbers stored in a double precision. So looking at these rules now that we're on the topic, so sometimes a copy is made, sometimes both the objects share the underlying data, and this is now the difference, that when you slice a Python list, the result is always an entirely new separate object, whereas the numpy slices, they share the underlying data, because when you slice a humongous matrix, so if every such operation created another humongous matrix, so numpy is supposed to be efficient in memory, so there is the method copy. So from any numpy array you can always create a separate copy of its contents if you need a copy, but in the spirit of using as little memory as possible, so two objects using the same underlying data, they set to be views to the data. So data is what it is, and when it's viewed through different lenses, so the very same bytes, they could look like a 2x1 array, or they could look by a 4x5 array. So it is, things are the way that you look at them. So again, bit of Alan Watts spirit in here. And then another difference illustrated with this one. For example, Python plus, because it works for arbitrary list, is concatenation, cannot be element-wise addition, because lists don't need to be the same. Whereas in a numpy, its plus is not concatenation, but is the element-wise plus, and the multiply is the element-wise multiplication. And notice that this is now different from matrix multiplication. You wanna use the dot product function, so it works magically. We think of dot product as a vector function, but that takes us to the next beautiful thing in the numpy design, that when you do something that like dimensionally wouldn't be legal, like for example here, I took 2x10 and multiplied it by a scalar. So normally these operations expect that the dimensions are the same, because this happens element-wise. But this now what is called the broadcasting in numpy means that if the one thing doesn't have enough dimensions, so then these operations pretend that it is as if these had been duplicated across the dimensions, that initially this is a 1x1, so then it's expanded to be a 10x1, and then it's expanded to be a 2x10, so one dimension at a time. Just by so of course this data is not redundantly copied in the memory. It is just that all these universal functions are smart enough that they behave as if the lower dimensional thing had been properly expanded. So here, for example, well, I don't know if it's possible to apply a trick to a matrix. That's above my pay grade and the calculus knowledge. But but at least, so what is a cosine of an arbitrary matrix? So element-wise. So all these functions operate element-wise. So notice that you gotta be careful that you always use the numpy version of a function. because some of these functions, they might also be in the language and the other standard libraries, so make sure that you're using the correct one. So keep the numpy arrays as numpy arrays, and then the final result, bring it back to Python if you so inclined. One more nice thing, so scrolling, so numpy is basically like you had a MATLAB inside Python. So it has one nice thing that this Python itself doesn't have. So this one is from the MATLAB. The MATLAB otherwise is like a primitive Python from a simpler time, but it had one thing that the Python doesn't have, but the numpy is here. So notice what happens if you do a comparison, the very same. So this is a higher dimensional thing, this lower dimensional thing is expanded across the dimensions. So this becomes an element-wise comparison, and the results are truth values, so individual 0 or 1 bits, which are true for the positions where this comparison is true and false otherwise. And then the fancy indexing. So when you index a numpy array with the equally sized truth value array, so then it cherry picks the MATLAB style the elements that are satisfy the condition. Let's see if we can do this. So we have this numpy array. So let's say we say all the elements that are greater than 3. So we get this kind of array. But I feel better if I'm gonna turn this into a single vector first. So now all the positions where element is greater than 3. Okay, and another teachable moment. So I want the shape to be one-dimensional. So I previously still made a two-dimensional 1 by 20, so that's a different than 20. So now notice which elements are greater than 3. So 3 is not 0, is not 4 is the first one, so that one's the true. And then, so if I let's create it on the spot again and use it as an index, looks kind of weird, but observe. So cherry picks the elements that satisfy a given condition. That's kind of nice.